So if I were really maximizing entropy, I'd probably just skip my talk to allow the widest variability in options for the rest of the time. But I don't maximize entropy, or at least I don't think I do. So I'm going to go ahead and go through at least some of my talk. And I'll give away a little bit of the point in the outline. So I want to do a little bit of framing, just so you know where I'm coming from with my background and experiences. And then I want to talk about 3 specific examples that I think illustrate the role of cognitive science in AGI. We can debate whether the examples actually illustrate something interesting about AGI or whether it's something different, but I think they're at least in the same spirit, and then some conclusions. So I thought first it would be useful to put up what I found on the websites for what the different groups are about. So that definition of what AGI is all about is on the AGI website. And the focus of cognitive science on understanding the human mind was mentioned a couple of talks ago. So I think that there's some relationships there and that there's some commonality. It's also the case that I think that the goal among at least a subgroup within cognitive science to develop integrated theories of cognition, of human cognition, is well aligned with the goals of AGI. And one of the things that came up a couple of times throughout the course of the conference here is the issue of whether or not it's a good idea or why it might not be a good idea to pursue lots of micro-theories in the hopes that eventually we get enough of them to build a more complete theory of mind. And at least one of the issues, or maybe 2 of the issues involved in that, is something called the identifiability problem. It's just, there's this fact that the implementations that we have of our theories are very detailed. They make very specific predictions about performance. And the data we have available to us to evaluate those theories is insufficient to either prove or disprove them. And there's 2 sides of this. One side is that you can have lots of different theories that produce identical behavior and performance. And so how do you distinguish between them as being right or wrong or more or less successful? And there's actually a massive space that we can look in for developing algorithms to produce intelligent behavior. And so finding some way to constrain that space so that it becomes something less than infinite is perhaps useful. And so, so my bias in the work that I pursue comes from Alan Noel and the work that he did across several decades. Much of it sort of characterized in the book Unified Theories of Cognition. And just quickly, a quote that shows up in that is up on, I don't know if I should read it or not. Probably for the sake of time I won't, but go find a copy of the book, look at pages 17 and 18. The point here is that you don't want to look at isolated theories. You need a theory of the entire system that we think of as mind. You need to know what the parts are, and you need to know how they fit together. I actually ran a workshop a year ago at CogSci in Berlin on this very topic, looking at your integrated theories. Yes, I'm guilty. I'm a cognitive scientist, so the word human is actually in there. So integrated theories, integrated models of human cognition. A couple of people here actually presented there. So there is some crossover already between these communities. But just to go a little further in exposing myself as a cognitive scientist, this is from a talk that Alan Noel gave in December of 1991. In that talk, he referred to ultimate scientific questions. Those are questions of a depth that they can hold you for an entire life, and you're then just a little ways into them. And this is the slide that he presented. The question for him was the nature of the human mind. I think I share that with him, but and he referred to needing the details in order to actually understand the mechanism and what's going on under the hood. What the question was for him is how can the mind exist in the physical universe? But he also raised a number of questions that it was not, and I'll just highlight the question that he thought it was and one of the questions that he thought it was not. So there is a distinction, I think, between the cognitive science and AI communities in terms of the ultimate questions that they're pursuing, but it doesn't mean that they can't share and interact in finding an answer. And as Alan Newell said, the answers to those questions may in fact actually be the same. And I think that goal actually reflects very well what the goal of the Cognitive Science Society is. So recently, about 5 years ago now, I guess, maybe that's not recent anymore, there was a symposium at the Cognitive Science Conference talking about fundamental questions in pursuit of the goals of cognitive science. It was a collection of people who had won the Rummelhart Prize, which is the highest prize for the Cognitive Science Society, and each of them provided what they thought was a critical, fundamental question that cognitive science needed to answer in order to understand the human mind. And the point of showing these is just to illustrate that a lot of the questions that are relevant to understanding the human mind or are relevant to cognitive science are actually quite relevant and extraordinarily important to understanding minds in general. So things like, where do features come from? What is context? What is the nature of immediate discourse and the transition from sentences to discourse? This question was an interesting one. What will cognitive science be like after the singularity? This wasn't about the singularity. The singularity that was being talked about here is, what do we do when our models of the mind become too complex for us to understand? And there were some examples where there were models that were making predictions that the person who built the model couldn't understand. And so what do you do then? Build a model of the model? Give up? Declare success? All sorts of options. And the list goes on. If you want to know what these are, you can send me an email or catch up with me afterward, and we can go over them. So that's just a little bit of framing about the background I come from and some of the things that I think of as being important in pursuing an understanding of cognition. I now want to go into a few examples of the ways in which cognitive science and AGI sort of come together and what the role is of cognitive science in building more general theories. And I'm going to do this by way of three examples, and because of where I come from the Air Force Research Laboratory in the United States, these examples come from actually using the theory. So we want capabilities to come out of our understanding of the human mind that we can use in various ways. And the first one is work that I've done personally, which is understanding the effects of fatigue on cognition. Somebody said they had a really old quote, but I think I beat him, so this one's almost 100 years old. The quote is, "Mental fatigue is one of those scientific problems that has suffered from too much practical importance." And so the story here is that fatigue, well, first of all, it's dominant. So if you want to address real-world fatigue-related issues, understanding the way fatigue in fact impacts people is absolutely critical. And it's the case that fatigue really does impact people, and it has lots of very serious consequences in the real world. And so a question might be, is this really AGI, or is this just developing an application? Well, this is actually an example, I think, of the identifiability problem. So there's lots of things out there. There's countermeasures that we have, various drugs that we can put into our bodies that help us stave off the effects of fatigue. Lots of coffee was served at this conference. Lots of people were drinking it, and that helps you perform even when you're tired. There's education programs, there's regulations that limit work schedules for people like long-haul truckers and long-haul airline pilots. But they're all sort of one-off solutions to the problem that don't address the real underlying causes or provide a unified, comprehensive way to address the issues. And so in order to do that, you need something that's, in order to develop a holistic solution, you need to have a broader theory. And to do that, reuse is going to be necessary because building that from scratch ends up being challenging. And I think that this reuse issue illustrates a problem that's been raised in psychology, but I also have seen glimmers of as I've watched the proceedings here. And so it's a critical barrier to reuse is something called the toothbrush problem. Who knows what the toothbrush problem is?
Yuck. The yuck issue.
Nobody? Yosha does. Oh, then you weren't listening to my talk a year ago, so I'm going to remember that. The toothbrush problem is simply stated, theories are like toothbrushes. You don't want to use anyone else's. And so in the context of building something like an AGI system or a unified theory of cognition, that leads to real serious problems, because if we're unwilling to borrow ideas and borrow theories from other people, then we're stuck in a position where we have to build everything from scratch at each new point in time when we want to broaden and expand. And that ends up causing weakness, and it's a barrier to progress, because there's lots of good work that's been done in the past that we can build upon in building broader, more general, more powerful theories. So, and this was raised by Jay McClelland in the inaugural issue of Topics in Cognitive Science, because different people like different theories, they fight about them on the margins, they focus on areas where theirs has strength, and everybody works in isolation. That ends up causing problems. So in the case of fatigue, we developed a mechanism that we integrated into the ACT-R architecture. We validated it carefully using some very detailed laboratory studies of human performance. We generalized that out to other domains like driving and flying. And the goal is then to develop the basis in order to, and in addition to doing that work, we also were integrating across a variety of other theoretical domains and areas, drawing upon sleep research, drawing on other cognitive science research, etc. And the goal here is to develop technologies, capabilities where we can do fatigue risk management and develop fatigue monitoring systems that allow us to look at the person as a whole and identify ways of both designing systems and monitoring people that reduces the likelihood of really bad things happening to them when they get tired. Because we live in a world where you can't schedule fatigue out of human beings. We're up too late, we're up too early, we're up all night, we're crossing multiple time zones in hours instead of weeks. And so our bodies simply can't adapt to the environment that we're being put in. And so we have to do something more than just adopt a scheduling restriction. So that's that. The other ones will go faster. So the primary area where the group at the Air Force Research Laboratory that does cognitive modeling works is in the area of training. This is sort of a big monster diagram to illustrate the way that we see training occurring. And there's a variety of ways in which models of people fit into this framework. So understanding the way that experts represent knowledge and skills and what those knowledge and skills are that are required to do various tasks. Supporting the training environment so that we can have large-scale training experiences that are realistic and credible, even when we don't have enough people to fill that all in. Representing instructors, so one of the most successful applications of cognitive architectures and cognitive modeling is in the context of intelligent tutors. So developing those so that they can look at trainee behavior and assess the knowledge and skills that they have and what they need to know, and then use that to drive later training interventions. And at the center, developing algorithms for understanding, learning, and forgetting that happens on long time scales in order to be able to track what a person knows and what we expect them to know in the future, so that we can schedule training around those needs rather than around a calendar and a date. One of the things that we're working on specifically is the development of synthetic teammates. So this is a capability to plug an artificial agent into a training environment. Because it's operating as a teammate, it needs to do weird stuff like communicate with human beings. It needs to be able to take in communication from human beings and interpret that in the context of the task that it's doing, in order to make decisions, in order to take action, in order to perform the task. And so we've developed a model that stands in as a pilot in the context of a 3-person team that does reconnaissance missions in an unmanned aerial vehicle context. And they communicate through natural language text chat, unconstrained. The model is able to interpret that language. It currently functions on par with state-of-the-art parsers, except it doesn't need an upfront tokenizer in order to do that parsing or to understand the text. It then takes those parsings and interprets that in the context of the task, at the state it is in the task, and uses that to drive its piloting behavior to make sure that the scenario goes as planned and they get as far along as they can. Okay, so that was an example where I think understanding the human cognition is essential. If you're gonna build models that are playing those kinds of roles in training environments, then understanding human cognition and in some sense matching to that ends up being important. And then the other way that human cognition matters is serving as an exemplar. And this also came up earlier. So if we're going to build if we're going to build an AGI, then having an example that functions as an AGI could be helpful in constraining our theories. And so another area that the Air Force is working is in the context of autonomy. So the world's a complex place. It's getting harder and harder to communicate. There's lots of stuff to do. And so having technologies that are able to function as well as or better than people in domains that are currently done by people is a desirable direction to go. And the specific area where the Air Force is focusing is on this thing at the bottom, integrating machines with humans seamlessly, so that they're maximizing the performance of the human-machine system as a whole in order to get things done as well as possible. There's a couple of levels to this. One area that we're working is in human-machine collaboration and decision-making. So this is a project that's looking at comparisons of what you can get out of machine learning and comparing that, running that side by side with a human doing the same task, so that we can understand the way in which human and machine decision-making and learning may diverge with experience, and how we can either use that advantageously to make better decisions, or how we can use the machine learning algorithms to inform the way that people are making decisions to help them come along to better decision-making procedures themselves. There was a report a couple of years ago by the Department of Defense on the role of autonomy in DoD systems, and it sort of spelled out the way that the Department of Defense thinks about autonomy. It's okay. In this report it says autonomy is a capability or a set of capabilities that enable a system to be self-governing. And autonomy exists on a continuum where it's either from completely human controlled up to completely autonomous. And what autonomy really is about, it's about how to allocate responsibility across humans and machines in a human-machine system. So don't be fooled by names. So that's an unmanned air vehicle. It's in no sense unmanned. It's teleoperated. So it actually takes a team of folks to accurately pilot and maneuver that aircraft. And as you want to actually utilize that capability, it takes a lot of people to actually fly and operate and make use of an unmanned aerial vehicle. So just the point is that we don't have autonomy yet in that context. Another area where we're working is in looking at intelligence data to try to help intelligence analysts to do their jobs more efficiently. This is a picture of something that's called GMTI data, which is ground motion track information. What you see on there is a bunch of dots. The dots are actually things that are moving. So the way GMTI data works is it basically represents a Doppler shift on the ground or at whatever you're looking at. So all of the grayscale stuff is background, and then superimposed on that is all the stuff that's moving in the environment. There are some algorithms that can look at these kinds of data and say, hey, that's weird, or hey, that's weird, or if they have information about what the roads are and where they are and speed limits and all that, hey, that part's speeding, hey, that's speeding. What they don't do is make any sense of that data at all. And we get lots of data, or we have the ability to get lots of data like this, and we don't have enough people to actually look at all of the things that are abnormal or unusual and make assessments about why something is happening. Why is that thing speeding? Why is that going in the wrong direction? That sort of thing. So we're developing models that are able to look over lots and lots of those data and reason about it in human-like ways to come up with hypotheses, and then go back into the database of information to look for evidence to either support or refute that. So, and the way that we're doing that is with an architecture that we call CSAP, cognitively enhanced complex event processing. Complex event processing is a technology that's used out in industry, that's used for things like tracking stock markets and deciding when to buy and sell. We're augmenting that with capabilities to sort of capture what we know and like about human cognition and bring that into that space. Now it's got a lot of labels up there for what it represents, but if you look under the hood at what those things actually are, they look a lot like the kinds of capabilities and the kinds of things that have been talked about here and get talked about in cognitive science. So we've got world knowledge, we've got semantic networks, we've got procedural knowledge represented essentially as rules, finite state machines that are representing other information, etc. So just a little teaser on that. And then just to quickly wrap up, I just want to point out that I said early on that we're interested in capabilities, we're interested in mechanisms too, and sometimes I worry that the hype cycle associated with brand spanking new technologies for everything you ever wanted to do and more end up distracting us from some of the hard science that needs to be done in order to achieve the goals that we have in AGI and other areas. So you can find some of your favorite AGI-related terms up there. Maybe you like some of them, maybe you don't like others, but you know, there's a reality out there, and sometimes it takes a number of years before people really appreciate what capabilities those new emerging technologies really offer. I had to put this up, so I added this because I thought that this was interesting for those of you who are curious. There was a list that's related in a variety of ways that was put out something like 35 years ago by Alan Knoll in a paper. So you can look that up and see it. It was also the basis of a paper by John Anderson and Christian Labiere proposing a set of evaluation criteria for judging unified theories of cognition and the extent to which we're making progress on achieving them. So that's something that you could potentially look at. Maybe AGI doesn't care about all of those things, but I think many of those things either are explicitly or ought to be relevant to the goals that you're pursuing. Here's another way to look at it. This is a list of areas that ought to be covered by a unified theory of cognition, again proposed by Alan Knoll in his 1990 book. And what I think is interesting is that a lot of what happens in cognitive science and AGI and AI and other areas tends to focus on capturing the power of cognition, but there's lots of subtlety to what people do as well. And I think the subtlety of human cognition and the subtlety of mind is really at the core of what's needed for AGI and for cognitive science. So, quick conclusions. CogSci and AGI are not mutually exclusive. They can inform, inspire, and support each other. I think one of the things that's necessary is that they need to focus on integration and application of models to increasingly complex domains. And just a quick Posthoc plug. Recently there was a cognitive modeling ideation challenge The results of this were presented at the Cognitive Science Society a couple of weeks ago here in Quebec. And you can read what that cognitive modeling ideation challenge was about and what it was looking to achieve. So I think there's opportunities here to find other communities to team up with or engage with in order to look for ways to accomplish the kinds of things that AGI is interested in doing. Thanks.